You've run the numbers. You sit in the boardroom and tell the executive team the new product has a 60% positive sentiment rating. Then, the lead executive leans forward and asks the one question every data scientist dreads: how sure are you? Suddenly, that isolated 60% looks incredibly fragile. It's a single data point hanging in the air, completely defenseless. That single number is a piece of descriptive statistics. It does exactly what it says on the tin. It describes the exact limited set of survey results you've physically collected and counted. But the executive doesn't actually care about those specific survey respondents. They are demanding inferential statistics. They want you to take that small sample and use it to predict the behavior of your entire unseen customer base. A naked summary statistic can never bridge the gap between what you measured and what you were trying to predict. To actually answer the executive's question, you need to build statistical armor around your guess using 3 very specific tools. The first step in defending your metric is mapping the actual shape of your raw data. A normal distribution clusters symmetrically in the middle, but outliers can pull the average, creating a skewed distribution that no longer represents typical customers. Or a bimodal distribution hides 2 completely different groups, lovers and haters, disguised as one dataset. Handing leadership a simple average when your data looks like this is mathematically accurate, but functionally a lie. You have to verify the shape of your distribution before making any business claim. Once you know your shape, you hit the core inferential problem. How do you mathematically prove that your limited survey sample accurately reflects the vast unseen reality of your entire market? You rely on a mathematical principle called the central limit theorem. If you scoop multiple random samples from a chaotic dataset, the averages of those smaller groups automatically arrange themselves into a perfectly smooth, predictable bell curve. This mathematical certainty lets us calculate a confidence interval, a protective range around our estimate. But we have to be specific about what this means. A 95% confidence interval does not mean there is a 95% probability the true number is inside this bracket. It means the mathematical method used to calculate this range works correctly 95% of the time. This transforms a fragile, isolated guess into a quantified range of reliability. It gives your metric the armor it needs to withstand boardroom scrutiny. So your baseline is defended. Next, leadership approves a new app feature designed to push that 60% approval rating even higher. After the launch, the numbers go up. But you need an A/B test to prove that your new feature actually caused the increase, rather than the data simply experiencing a random daily fluctuation. To do this, mathematically, we start from complete skepticism. We build our test on the assumption that the new feature did absolutely nothing. We then introduce a metric called the p-value. This calculation measures our final app data strictly against that baseline assumption of 0 impact. This is where we have to correct a massive industry misconception. The p-value is not the probability that your new feature was a success. The true definition is stricter. The p-value tells you exactly how surprised you should be by your resulting data if your feature was completely useless. We return to the boardroom. The executive asks the exact same question, but this time you are equipped with the full statistical toolkit. You lay out the complete defense. You show how the distribution shape maps the reality of the user base. You present the confidence interval that mathematically guards your estimate, and you deliver the A/B test that proves the new feature drove the results. Handing over a descriptive summary is asking leadership to take a leap of faith. Wielding inferential statistics forces the data to provide the proof. Data science is ultimately the measurement of uncertainty. When stakeholders ask how sure you are, your answer rests on a foundation of mathematical evidence.